So, from our last session, we understand that our sequential statements are going to be inside of a process body. Here, let's talk little about the process syntax. In the left side, you can look over the syntax first, and then in the right side, you can map that with the example of a multiplexer function. Till now, I am assuming that you are already familiar with the VHDL entity and architecture, so that I am not repeating the same here again. If you are not familiar with those, then I would recommend you to go through my previous sessions on these topics. I will paste the link in the description for ease. Okay, the syntax is we start from the process label followed by the colon symbol. This you can treat like a process identifier, which tells that what is this process all about and what function you are going to design inside this process. This is very important, especially when you have many processes inside your architecture. And this label will help you and others when going through your VHDL code again in the future, or when you are discussing your code with the teams, etc. You can also mention that in the comment section as well, but VHDL allows you to write a label for that. So I recommend you to make this practice to always write the label when you describe any process. Anyway, this is completely optional, so if you don't write the process label, then it won't make any difference in your simulation results and synthesis results. Okay, next we will type process and write all the signals which are inputs to your process. These signals can be the interface signal of your module or can be the internal signals as well. And these should be written inside the brackets and separated with comma. This list we call the sensitivity list, and this is very important to list all the signals which are inputs to this process. If you don't do so, or if you missed any signal to write in the sensitivity list here, then your simulation results may not be the same result which you are expecting, and you may wonder that you created the right logic but still not getting the right simulation results, right? So make sure the sensitivity list is correct. We will be understanding this with the example in some time. So no worries if you are still unclear, just be with me here. Let's continue to our syntax again. Once you write the sensitivity list, then type begin and then write all the sequential statements for your function. Once you are done writing your function, you must need to end the process. So write end process and semicolon to end your process. You can write the process label identifier before the semicolon if you want. Let's move to the example in the right side. It is the simple multiplexer. So we written mux function, which is our process label, then colon and write process and type a, b, select in the bracket. Then type begin and start writing your function. So type if select is equals to 1, then dout gets the value of a, else dout gets the value of b, semicolon, and if semicolon and process semicolon. Till now we made this concept that when you are writing the sensitivity list for the process, then you must list all the inputs here. And if you do not do so, or you miss writing any input in the sensitivity list, then you may not get the expected results from your simulation. In this slide, we will understand that why sensitivity list is so important and how it affects your simulation results, and why this concept was designed. The reason why this sensitivity list is important and why it affects your simulation results, the simple answer is because those sequential statements which you write inside the process do not execute all the time. It will only execute when at least one input from the sensitivity list changes, and it is logical too, because if no input changes, then no output will change, right? So there is no need of executing those statements inside the process when no input signal for that process changes. And it will help simulation tools to simulate fast, especially for the large functions or large digital system designs. Another aspect of the sensitivity list is that it won't affect the synthesis results much. So if you missed any signal to write inside the sensitivity list, then your synthesis results or the schematic structure may not be different. But you will encounter another problem. Can you guess what it could be? The problem would be that your simulation results from the VHDL function won't match with the simulation results of the gate level simulation. And the design you created in VHDL may not act same when you configure them into the FPGA or ASICs. Big problem, right? Because your system not working same as you are expecting from it. Now, if you get little understanding of the sensitivity list, then try to figure out what will happen if you miss to list select input inside the sensitivity list. Give a pause here and think a while about the simulation result. In this screen, these two VHDL codes are exactly same except the sensitivity list. So compare the left side process, which include all inputs in the sensitivity list, and compare this with the right side process, which don't include the select input in the sensitivity list. Did you answer that behavior simulation result will be same for both the VHDL codes because we written the same behavior for both the functions? But sorry to say, but we won't be getting the same behavior for these two functions. Right one with missing signal in the sensitivity list will no longer give you the results of a multiplexer in the behavior simulation. Reason is, if you change input select, these statements will not execute. And because these statements are not executing, how you will get the results in the output screen? These statements only executes when input A or input B will change. So if an input signal from A or B changes, then only you will get the behavior of a multiplexer from the right side VHDL code. But if only select input changes, it won't act as a multiplexer in the behavior simulation. Now, if we talk about the left side VHDL code, those sequential statements will execute when any input signal from A or B or select changes. So you will get the correct simulation results. In this slide, let's review our design and behavior simulation when we have all the signals listed inside the sensitivity list. Give a quick check to the simulation results in the right side. We will look over the yellow markers and their values. So in first image, select input is 0, means the out should be same as input A, and input A is 0 here. So the output D out is 0. This is good. Now look into the second image. Here select input is 1, means D out should be same as input B, which is 1. Hence we get 1 at the output. This is correct too. So we notice that the behavior simulation results is correct and giving you a function of a multiplexer. And when you synthesize this, then you will get the same results. And even if you configure that into the FPGA, then you will get the same multiplexer function. In the next slide, we will see the synthesis results of this VHDL code. So this is the schematic result which synthesis tool created for us from the VHDL code written in the left side. Note that we included all the input signals inside the sensitivity list here. Of course, this is the gate level schematic of your multiplexer and will give you the same function of multiplexer when you configure this into the FPGA. And that result will be same as we seen in the behavior simulation in the last slide. Now in next slide we will not include select input in the sensitivity list and we will see how it will affect our behavior simulation. Left side is our VHDL code. If you notice, then select input is missing here in the sensitivity list. Otherwise this is exactly same as our last VHDL code. Now look over the simulation result at top right. Did you see the right function of a multiplexer? Then check these yellow markers where the select input changes but input A and input B are not changing. Did your output change or did it still behaving like a multiplexer? No, Because at this instances, input A is 0 and B is 1, and when select is 0, then we should get the value of A, which is 0, but we are still getting our last output. Why? Because these statements are not executed yet, so no changes in the output. You may get confused on this first image because you see the output Dout is 0 here. But this is not coming from the executed statement. This is just the last value which is continued as signal because that is not changed. Means in last change it is 0, so it is continued as 0. But you will notice the problem in the second image. Now look at the yellow marker in the second image. Here select input value is 1. That means from the behavior of our VHDL code, we should get input B as an output, correct? And input B is 1 here. That means Dout value should be 1 at this point of time. But we are still getting Dout as 0. Is this our expected behavior from our multiplexer? No. This means that this behavior simulation is not giving the right function of a multiplexer now. Well, I wanted to move your focus into the third screenshot now. So in this case, we changed input signal A as well. At the same time, we change the select input. If you see in the code, input A is listed in our sensitivity list. So now we changed both these inputs. Then our code inside the process executes and then we get the correct results here. Let's map it quickly. Select is 0. That means we should get input A as an output. And if you check Dout, then it is 1, which is correct. Because at this point of time, input A is also 1. But remember, this function, this time, our code executed because input A changed, not because input select changed. So it's just a coincidence here that at some point of time, when both the input signals get changed at the same time, then the statements gets executed. I hope you are very much clear on the execution of statements and sensitivity list importance. Now in the next slide, quickly look over the synthesis results which tools created for us for this VHDL code. Okay, look over the synthesis results. If you notice that this is exactly the same schematic like the last one. This means your synthesis results are exactly same. And because this is the gate level schematic of a multiplexer, then when you configure this into the FPGA, then it will act as a multiplexer. No matter whatever your behavior simulation results for your VHDL code, or if it is matched or not. Now you can argue that what's the matter if finally we are getting the right schematic and we are getting the right function when configuring the final schematic into the FPGA. But here is the problem, that the first step of checking your VHDL code of your function is the behavior simulation results. And if you don't follow the VHDL guidelines correctly, like here we did, we will not get the correct simulation results in the behavior simulation. And we will engage in just figuring out the reason for the problem. So question is, why you gonna configure your design into the FPGA till you see the right behavior in your simulation, right? Anyway, if you do so, you should expect the different results in the behavior simulation and gate level simulation, which is not correct to consider. You tracked it here just because this is simple known function. But when you work on your projects with lots of components and processes, then debugging of those errors gonna waste lot of your time. So remember to follow the right guidelines and syntaxes. You will be wonder that I have seen some VHDL newcomers intentionally not including some of the signals inside the process sensitivity list just to adjust the output in the behavior simulation results based on their design needs. And they become happy that the behavior simulation is giving the expected results. But when they configure that same design into the FPGA, they get surprised that their design do not act same what they seen in the behavior simulation. But now you know the reason. It's really difficult to explain those thought processes, so we won't spend time thinking that. But I will only say that you must follow the VHDL syntax and VHDL procedures for good design practices. I am just telling you all these stuff so that you will have deeper insights on how these products or these tools function and how VHDL works. This will help you when you are preparing for the interviews. And if someone asks you to debug the issues in some code which they gives to you, and at that point of time you can answer them better with a good reason and explanation. In this slide, we will quickly compare the simulation and synthesis results side by side. Left side is the results when you followed the right guidelines and mentioned all the signals inside the sensitivity list. Right side is the results when you did not include select input inside the sensitivity list. Let's talk about the simulation results first. Look over the left image. When select is 1, the out should get the value of input B. Here input B is 1 and we get the output D out 1 here. So it looks good based on our behavior description. Similarly, you can check for the other timestamps as well. When select is 0, D out gets the value of A, which is 0. Now look over the right side simulation result. If you didn't notice, then check at the current timestamp marked with yellow line. Here, value of select is 1, means we should get value of input B at the output D out, which is 1. But what we get at the output, D out is 0 here. So this is not our expected result. Now look over the two images in the bottom section. You will see two identical schematics here. You will wonder to know that second schematic at bottom right, we get it from the VHDL design where we did not add select input inside the sensitivity list. And when you compare it with the schematic in the left picture, you will see that both the schematics are exactly same. Hence, when you configure these VHDL design, then both the VHDL design will give you the same results because their gate level structure are exactly same. But if you remember that our simulation results was not actually same, and if we talk about the right side results, then it was not giving the correct results in behavior simulation because we missed to add select input in the sensitivity list. So this is a big problem here that your behavior simulation result is not actually matched with the gate level simulation results. Let's talk about few important process rules. The most important aspect of process is what we have just talked about, that is sensitivity list. And process will only execute when at least one signal from the sensitivity list changes. Another important thing to remember about the process is that the statements inside the process are sequential statements and can execute sequentially, means one by one. Because these are sequential statements, that means you need to follow the correct order of your statements. Wrong order may lead to wrong behavior or results in the simulation and later in the synthesis too. This is because assignment to the signal occurs based on the last assignment. Another important thing to remember is that process itself is a concurrent statement and that executes simultaneously with other processes and other concurrent statements inside the architecture. We will be covering this topic more with multiple processes inside the one architecture in this learning series. And definitely we will include this important aspect when we will design our projects later during this course, so that you can use using them very frequently. So stay tuned for the upcoming updates and meantime subscribe to the community and press the bell icon too so that you can get the notification whenever new post is uploaded. If you found this video helpful, please give it a like and leave a comment below and don't forget to subscribe for regular updates.